Hello, my name is Kyle Johnson, and my project is called the Pipeline Hazard Simulator. This project creates a cycle-level simulation of a 5-stage pipeline processor with hazard handling. The goal is to simulate the simplified 5-stage pipeline processor and measure how hazards affect the performance. The main questions are: how do raw data hazards affect pipeline timing? How much does forwarding reduce stalls? How do load use hazards behave differently? And how much do branch/control hazards increase the CPI? Our output metrics are the total cycles, the stall count, the branch penalty count, the CPI, as well as the cycle-by-cycle pipeline table. The simulator uses the classic 5 pipeline stages of the instruction fetch to the instruction decode/register read, to execute in the ALU operation, to memory access, and lastly the write back result. And our assumption for this is that each stage takes 1 clock cycle. After the pipeline fills, 1 instruction can complete each cycle, but hazards do interrupt that ideal flow and force stalls, as we'll later see. The simulator models 3 main hazards. Those are the raw data hazard, where an instruction needs a register value produced by an earlier instruction. As you can see in this example, the sub operation needs x1 that is used in the add operation. The second is the load use hazard, where a loaded value is needed immediately by the next instruction. Where you can see here the add needs the x1, whereas the LW instruction also previously used the x1. And lastly, we have the control hazard, where a branch affects which instruction should be fetched next, whereas this one requires the target as the next instruction. Here are our policies for the hazard handling. First is no forwarding and branch stall. We will say that the raw hazards cause the stalls, and the branches add penalty cycles. The next policy is the forwarding and branch stall. The ALU dependencies can be forwarded, but the branches still stall. And lastly is forwarding with no branch penalty. This is the idealized version with forwarding and no branch penalty. These are our test cases that we will be using. The first is the independent. The purpose is to have a baseline pipeline with no hazards. The next is the raw hazards for repeated ALU data dependencies. And then we have the load use for the load use dependency case. Then we have a branch hazard for branch or control hazard cases. And then we have the mixed hazard, which combines the load, raw, and branch hazards. And with these 5 test cases, they each have 3 policies, which leads to 15 simulation runs. And here is the mixed hazard case results that we will later see run. For the first policy of no forwarding in the branch stall, it went through 18 cycles with 8 stalls and a CPI of 3. For the forwarding and the branch stall, there was 13 cycles with 3 stalls and a 2.17 CPI. And then for the forwarding and no branch penalty policy, we had 11 cycles with 1 stall and 1.83 CPI. The main takeaway from this is that forwarding significantly reduces the raw stalls, but load use hazards and branch penalties can still hurt the performance. Now I'll show you the code. So the project is split into separate files. This first test cases file stores instruction traces, and each case is designed to stress a different pipeline behavior. So as you can see, we have the independent case is our baseline at the top, and then we have the raw hazards, the load use, the branch hazards, and the mixed hazards. And then next we have the instructions, which parses each instruction into an object with an operation, destination, register, source registers, and flags, such as like the load or the branch. And then we have the simulator, which contains our main pipeline logic. It checks whether the current instruction depends on the previous instruction. And then if forwarding is disabled, the raw hazards cause 2 stalls. If it's enabled, the ALU dependencies do not stall, but the load use hazards still cause 1 stall. And then lastly, the branches add a 2-cycle penalty when branch stalling is enabled. Then we have the visual function, which prints the readable timing tables. It saves the CSV files and creates the charts for all the outputs when the code runs. And then lastly, we have main, which runs every test case under every policy and then prints an overall summary at the end. So now we can run the main function, which is the main.py. So back up at the top, the independent case has no hazards, so all policies produce the same result for these first 3. And then we have for the raw hazards, it shows the biggest benefit from the forwarding. Without forwarding, it takes 14 cycles and has 6 data stalls. When we add the addition of forwarding, the total cycles drops down to 8 with 0 data stalls. And that remains the case for the forwarding with no branch penalty as well, because there is not a branch dependency present in this test case. And then we have the load use test case. For this one, it also shows that forwarding helps, but 1 stall remains because the loaded data is not available soon enough. So while the no forwarding and the branch stall causes 11 cycles, we are still at 8 cycles with the data stall for that policy, even though there's only 3 given instructions. So it still has a CPI of 2.67 compared to the forwarding branch of 2. And then we have the branch hazard. It shows the cost of branch penalties. We're not able to entirely remove the branch stalls until we go with no branch penalty, where it's able to complete in 8 cycles with the 2 CPI. And lastly, for the mix hazards, it's the most complete example. Without the forwarding and with the branch stalls, it takes 18 cycles with 8 total stalls and has a CPI of 3. With the forwarding and the branch stall, it improves to 13 cycles with only 3 total stalls and a CPI 2.17. And lastly, for the forwarding and no branch penalty, it improves to 11 cycles with 1 stall and 1.83 CPI. The reason that this one is lower CPI than some of the other examples is that this one has more instructions, so overall it's able to mitigate the effects of that starting setup for the instructions, where those first 4 stages where no instructions can complete. So this one, that 4 gets averaged out a little bit better when there's 11 total cycles, instead of some of the other examples where there's only 8 possible total cycles, but there's still those 4 setup stages. So that's how it maxes 2 CPI, whereas the combined is able to drop it down to 1.83. And then down at the bottom, it prints that overall summary, and then the simulator also saves these as output files. It saves the charts and tables that it generated as um, CSV files. And then the last part of it is the SymPy demo. It's used as a discrete event simulation component. And in this file, each instruction is modeled as a process moving through the 5 pipeline stages. And it performs through the simulator.py file. It just visualizes it a little different. Now we can run that file. And the output shows that as instructions enter the stage by the simulated cycle. For example, instruction 1 enters IF in cycle 1, then ID in cycle 2, while instruction 2 enters the ID stage. So for each cycle, it shows which instruction is entering which stage, just for a better representation of how many instructions are running simultaneously. So the main hazard analysis is done in the simulator function. This demo just shows the event-based pipeline timing concept. So this project simulates a five-stage pipeline processor and compares how the hazard handling policies affect the performance. And the results show that forwarding greatly reduces the raw data hazard stalls. However, the load use hazards can still require stalls, and branch penalties can still increase the CPI.